These 37 satellite galaxies are deeply unsettling. Almost all of them are facing towards the Milky Way, as if some invisible forces were quietly pulling them towards us. Only a single one hangs alone on the opposite side. This anomaly was discovered by the James Webb Space Telescope while observing the Andromeda Galaxy. Imagine throwing a handful of marbles at a tree. Normally, they would scatter in every direction. But this time, almost all of them landed on the same side. It feels as if probability itself is playing a prank. Scientists calculated that, under our current cosmological models, the probability of such an arrangement is less than 0.3%. Practically impossible. And yet, there it is, hanging in the sky, mocking the seemingly perfect equations of the universe. Even strangers. These satellite galaxies are arranged along an almost perfectly flat plane, neatly aligned towards the Milky Way. No matter how you observe them, the configuration violates the randomness the universe is supposed to have. So the question arises, what is pulling them? And what is causing an entire galactic system to tilt in such an unnatural way? Scientists tested models after models, but every simulation failed. In computers, satellite galaxies spread evenly in all directions. In reality, they are crowded onto one side. This anomaly has opened cracks in our understanding of cosmic order. Some suggested it was a trick of perspective, but when the viewing angle changed, when different wavelengths were used, the result remained the same. That means the bias is real. It is not a measurement error. It is a genuine anomaly. And so the scientific community began to suspect that something deeper was at work. A mechanism we do not yet understand. An invisible force, silently steering the orientation of galaxies. It emits no light, reflects nothing, cannot be directly observed, yet seems to dictate the layout of the universe itself. Once again, attention turned to the most mysterious entity of all, dark matter. Because without it, galaxies would fly apart, stars rotate too fast, structures are too stable, and scales are far too large to be held together by visible matter alone. Humanity began to redraw the skeleton of the universe, but a new problem emerged. Is this anomaly truly caused by dark matter? To answer that, we must first understand how dark matter cosmology actually works. In scientific models, the universe is an invisible web. The threads are dark matter. The lights and stars we see are merely dust clinging to that web. We saw the lamps, but what holds them up is beneath the dark framework. It neither shines nor reflects light. It does only one thing. It controls everything through gravity. Galaxies orbit within its grasp. Satellite galaxies line up along its filaments. The universe may appear chaotic, but behind it lies an unseen order, maintained jointly by dark matter and dark energy. But how do we know it truly exists? Scientists point to 3 lines of evidence. The first comes from galactic rotation. In theory, the farther a star is from the center, the weaker the gravity, and the slower it should move. But in reality, stars orbit at nearly the same speed. This implies an invisible mass, extending far beyond visible stars and gases, dragging them along. The second is gravitational lensing. When light passes through galaxy clusters, images are mysteriously magnified and distorted, as if space itself were being tugged. That unseen pull is dark matter, bending light and reshaping our views. The third is the structure of the universe itself. Matter is not randomly distributed. It forms a vast cosmic web. Dark matter builds the scaffolding first, and ordinary matter flows along it, condensing into galaxies. In other words, what we see is frost forming on an invisible framework. Yet something remains deeply strange. If dark matter is everywhere, how exactly did it influence the satellites of Andromeda? Scientists propose that every galaxy is wrapped in a massive dark halo, an invisible cloud whose gravity binds satellite galaxies together. If the halo is slightly tilted, or its density uneven, the satellites could be collectively pulled towards one side. creating the observed lopsided arrangement. That would mean Andromeda's anomaly is not coincidence, but the dark halo acting behind the scenes. The problem is, while we see the effects of dark matter, we have never captured it. For decades, humanity has built detectors underground, in space, inside particle accelerators. Every search has come up empty. It can pull galaxies, yet refuses to interact with any known particles, like a shadow you can feel, but never touched. So a deeper question emerges. If dark matter is not a quiet, passive mass, then could our entire cosmic blueprint be wrong? Scientists began re-examining every model, and cracks started to appear. At first they were tiny, like hairline fractures in a wall. No one noticed, but over time, they grew, until evening the foundation began to shake. The first crack was the missing satellites problem. The lambda cold dark matter model, the dominant theory of cosmic structure, predicts that galaxies like the Milky Way or Andromeda should be surrounded by thousands of small satellites. But when astronomers counted, they found only a few dozen. Where are the rest? Are our telescopes too weak? Or was the model wrong from the start? The second crack was even more direct. It lay at the hearts of dwarf galaxies. Theory predicts that dark matter density should spike sharply towards the center, like a tightening whirlpool. But observations show flat cores instead, as if someone pressed a mountain peak into a plateau. This is known as the core cusp problem, and it suggests something far more unsettling. Our understanding of gravitational distribution might be collapsing. The third crack is stranger still. Simulations predict satellites scattered randomly, like seeds thrown into the wind, but in reality, they line up in thin planes, rotating together in synchrony. That level of coordination should be nearly impossible in a cold dark matter universe. The fourth problem strikes like a hammer. Theory predicts certain dark halos should be massive enough to host visible galaxies, yet we see nothing there. Regions that should shine remain dark, as if the universe deliberately turned off the lights. All these problems point to the same conclusion. Our cosmological understanding is not wrong, but incomplete. The models explain the big picture, but failed in the details. Perhaps the deviations come from dark matter itself. Maybe it is not cold and silent. Maybe it self-interacts, transfers energy, or is not a particle at all, but a large-scale field. We have misunderstood. At this point, scientists realized they may have been looking in the wrong direction. We stare into the distant universe, trying to map its skeleton, yet forget that the Milky Way beneath our feet is alive. It is not a static sea of stars, but a machine in constant motion. Dust burns, supernova exploded, hot gases expelled, then pulled back by gravity. A ceaseless breath. Perhaps the answer lies not far away, but right here. The seemingly calm galactic disk is releasing enormous energy. Who is heating this stellar ocean? Who cools it? Over and over again, when scientists shifted their gaze from the cosmic framework back to the heart of the Milky Way, they discovered something astonishing. The galaxy is burning, not metaphorically, but physically. It is wrapped in gas, heated to millions of degrees, hot enough to ionize atoms, and glowing in X-rays. Where does this heat come from? And who keeps it alive for billions of years? The answer lies between stellar birth and stellar death. Massive stars live fast and die young. In their final moments, they explode as supernova, blasting surrounding gas into space. Before that, powerful stellar winds stir the interstellar medium. The galaxy exhales. Over time, this energy accumulates, heating the space above the disk into a thin, invisible mist. It emits no light, but leaves subtle fingerprints in background radiation. Yet this gas does not escape forever. Gravity waits in silence, pulling it back. As it cools, it condenses into heavier clouds, then falls back towards the disk, fueling the stars. Astronomers see this and fall as absorption lines in distant quasar spectra. gas plunged inward at tremendous speed. This is a cycle, a breath. The Milky Way exhales matter, then inhales it again, sustaining its life. But something remains odd. If the gas returns, why does the outer heat remain so intense? Deeper observations reveal a second, even hotter layer, tens of millions of degrees, extremely diffuse, almost transparent. Stellar winds alone cannot sustain such heat. This energy must come from deeper, more concentrated sources, perhaps ancient starbursts, or long past galactic collisions. More surprising still, the heating is asymmetric. One side burns hotter than the other, like a furnace with a misaligned vent. This means outflows and inflows are also tilted. Combine this with a slightly tilted dark halo, and gravity no longer pulls evenly. Heat pushes, cold falls, gravity tugs. Over time, the galactic disk warps. Its edges lift gently, like fabric caught in the wind. Gaia satellite data confirms this. The Milky Way is not a flat record, but a warped vinyl disk. Stars rise and fall at the edges. The plane itself ripples. Who pressed it? Simulations show that even a slight tilt in the dark halo is enough to slowly bend the disk, not through impact, but through persistent, patient pulling. Like a trampoline, raised just a little on one side, the motion changes everything. Over billions of years, this gentle force shapes the wave-like disk we saw today. Such warps are common. Nearly half of spiral galaxies show them. The Milky Way is not unique. The pieces finally aligned. Dark matter is the unseen hand. Internal heat makes the galaxy breathe. External clouds stabilize it. Together, they created a system that is slightly distorted, yet remarkably stable. But structure alone is not enough to survive. The galaxy must keep breathing. Each year, it forms roughly one sun-like star. That requires hydrogen fuel. Where does it come from? Who delivers it back to the disk? Astronomers answered this by using background light. Distant quasars act like flashlights. As gas clouds pass in front, they leave fine absorption marks. Later, Hubble used nearby stars as backlights. The result was clear. More than half of these ionized clouds lies within 10,000 light-years of the disk, close enough to feed star formation. They are falling. This is not random rain, but long-term weather. Gas is expelled, cools, and returns. A breathing cycle. Chemical signatures may soon reveal whether this gas is primordial or recycled. Future ultraviolet telescopes might settle the question. The mass involved is enormous. Over 100 million suns. Enough fuel to keep the galaxy alive for a long time. Yet even this process is uneven. Some regions received more fuel, others starve. Once again, an unseen hand seems to guide the flow. At last, the life cycle closes. Heat drives breath. Clouds deliver fuel. Dark halos shape form. Everything moves, yet everything cooperates. And that raises the final question. Is this order purely physical coincidence? Or is the universe actively maintaining its balance? Galaxies breathe, systems drift, then return to equilibrium, not by command, not by intention, but as if stability itself were written into the fabric of reality. Perhaps the universe is not inert. Perhaps it lives differently. And perhaps, when we think about the universe, it is the universe thinking about itself through us. If that is true, then the Milky Way's gentle curve is not just gravity at work, but a system continuously adjusting itself, quietly, patiently, alive. And the deeper we look, the harder it becomes to believe that all of this is merely accidental. If the universe is sculpting itself, then what, exactly, is it trying to become?